All right, my little ducks. So this one is going to be the first video, and this one's really going to start to look at the reactivity lab, okay? And the reactivity lab, you mainly reacted metals, okay? So again, these are going to be on the left of the periodic table, okay? And because of that, all right, because they're metals, okay, they are most likely going to be following the trend of ionization energy is what we're going to talk about a lot in this video. And then electron affinity is not a trend you guys need to know. It was talked about in the video from Friday, but this would also tie in with it, okay? So nonmetals bond, they want to gain electrons to fill their outer shell, okay? The reason for that, when we look at the periodic table, all right, okay, when we look at the periodic table, all right, our metals are all to the left of what we call the stair step, okay? And what divides that is metalloids, okay? Non-metals generally have 4, 5, 6, 7, or, 8 with the noble gases, but we do ignore those for reactivity because they won't react, okay? They normally have 4, 5, or 6 electrons. It is valence electrons. It is so much easier for them to gain an electron to become stable, okay? Multiple electrons to become stable. When we look to the left, all right, our number of valence electrons is going to be 1, 2, 3, all right? They are more likely to lose to become stable because it takes a less amount of energy, okay? So when we're looking at the reactivity lab, we're dealing with those metals to the left. Okay, so when metals bond, they want to lose electrons. And again, that's because nonmetals generally have 4 to 7 valence electrons. I'm ignoring the noble gases right now. Those are still nonmetals. Okay, or metals have 1 to 3 valence. Ooh, that's not a 3. 1 to 3 valence electrons. Okay, all right. So any compound with a metal, okay, we're going to call an ionic compound. And that was talked about in the start of it, okay? They're commonly called salts, okay? And metals want to, again, we're really looking at lose electrons here and gain electrons here, okay? I am going to skip over the middle, the protons, neutrons, electrons, and orbitals. If we need help with that, let me know. Aluminum, again, we're looking at how many valence electrons. And the reason we want to use this model to look at reactivity is because it's going to give us a good indication of, hey, how many valence electrons do we have? How many valence electrons do we need to gain or lose? And my stuff just froze. Okay, there we go. All right, magnesium has 2. Tin has 4. Okay, sodium has 1. All right, and that is a good indication of how reactive they're going to be. All right, again, we're trying to lose this electron. So the trend that it's going to follow, okay, and coincide with is ionization energy, because it's all about the amount of energy it takes to steal those that one electron, an electron. Okay, that is ionization energy. This is just talking and writing. Okay, because of that, okay, metals, all right, and if you look at the trend, you can follow the trend on your note sheet, metals have a lower ionization energy because they want to lose their electron. They're like, please come take our electrons. We just want to be stable, please, okay? So their ionization energy is low because they want their electrons to be stolen, okay? They are, putting their electrons out, leaving their doors unlocked, doing everything they can to have an element come and take that electron, okay? Our nonmetals, okay, and if you look at the trend on the periodic table, it totally lines up. Our nonmetals have a very high electron affinity. Again, remember, it's going to increase going up, okay? Have a very high electron affinity because they're like, no one's touching our electrons. If anything, we want to gain them, okay? So when we look at the reactivity, okay, we'll notice that the most reactive is going to be sodium. That one can boom in the water, Okay, then it's going to go magnesium, aluminum, and then tin didn't react with anything in your lab. Okay, so this is the most reactive. It also has the lowest ionization energy, easiest to lose one electron. Okay, so a couple reasons. Most reactive, has the lowest ionization energy. It's the furthest to the left. Okay, it only has one valence electron it needs to have stolen, so we're only looking at first ionization energy here. Okay, so it'll very easily lose it. Tin, yes, is a metal. It has the highest ionization energy out of the group, meaning it's going to be the least reactive. And again, the reason for that as well, it would have to either gain 4 electrons, or because it's a metal, it will most likely lose 4 electrons. And that takes a lot of energy to pull off those electrons. Okay, so again, you can look at the valence electrons, but know that for metals, that valence electron, the fact that the closer we are to 0, the more reactive, is because of ionization energy. Okay, the closer we are to 0, that group 1 has a much lower ionization energy than, let's say, like group 3. Okay, it's also a lot easier to only lose 1 electron than it is to lose 3. Okay, again, the least reactive elements in the periodic table are noble gases. They have 8 valence electrons. They also have the highest ionization energy. They will not share. Okay, and again, that plays into reactivity because the closer an element is to having 8, the more reactive. And remember, it could be 8 or 0 technically when you look at it, because when they get to 0, when sodium loses that 1, becomes an ion, that outer ring disappears. Okay? All right. This very last one, and I'm going to try to keep these videos short, so I'm sorry it's so long, but hopefully this has helped us understand the tie between ionization energy and the reactivity of metals, okay, and valence electrons. So when we look at reactivity of metals, you can rank the reactivity based off of their number of valence electrons. It's very easy. The lower the number of valence electrons for metals, only metals, we're looking to the left right now on the periodic table. The lower the number of valence electrons, the more reactive they are. Okay, this is due because the ionization energy gets lower. It's easier to steal their electrons. Okay, all right. So that would be your answer to this part of this. Okay, all right. When we look at non-metals, all right, our trend becomes different. The reason for this, they need to gain or share. They need to gain or share to become stable, all right? They're not going to lose. They, again, we're looking 4 to 7 valence electrons, okay? Again, noble gases are non-metals. Miss Edge is ignoring them because they are not going to react, okay? Because they need to share or gain, okay? When they gain, what this causes is a super high ionization energy because they won't lose electrons, all right? And they also have a super high, they talked about it in the video a little bit, okay, electron affinity, which is like how likely an element is to gain an electron, okay? They will also share to become stable. What that means is they will also have high electronegativities because they're trying to pull electrons. Okay, either single electrons to completely gain it, or those shared electrons. So I am going to do a little bit more of a video on reactivity in the later videos, but hopefully this one gives you a nice little good start going over this reactivity lab and kind of helps link that ionization energy with metals.